Hi, and today we're looking at something called uncertainty. We're going to look at how this applies to your 12 required practicals, what you should do in your lab book. We're going to look at how you might get asked about this in an exam. Now, before we consider uncertainties, what we need to be clear of is, are we looking at a reading or are we looking at a measurement? So what is the difference between a reading and a measurement? Well, a reading is something where we're just looking at one value. So for instance, on a thermometer, when we look at the temperature of something, we're just looking at one place on that thermometer. We're not looking at whether it starts at 0. We can rest assured that the manufacturer has placed 0 correctly at 0. So that would be a reading. A measurement would be where we have to look at two ends of our scale. So for example, when we use a ruler, we need to line the 0 up at the right place and then we take the reading at the other end. When we use a protractor, we have to line the 0 up at the right end and then use the other end. So that is a measurement. You're taking into account two ends of the scale. Just to be clear, let's have a look at some more examples. Okay, so as discussed, we've just said that a thermometer relies on one judgment. So we're just looking at the top of the thermometer, so we're going to say that that's a reading. A ruler, however, we need to make two judgments, that at 0 and that at the actual length. So that is a measurement. A measuring cylinder, well, we never look at the 0, we look at the top bit, so that is a reading. A stopwatch. Well, a stopwatch, you have to know when to press start and when to stop. And so that is actually a measurement. A digital balance, we can rest assured that the manufacturer has calibrated that 0 is 0, and therefore we know that that is a reading. And a colorimeter is the same, that is a reading. And this is so important when we're looking at uncertainties, because the way you'll consider an uncertainty for a reading is very different from the way you'll consider an uncertainty for a measurement. Let's consider a ruler, and the smallest division on this ruler is 1 centimetre. In other words, it has a resolution of 1 centimetre. So I carefully place the 0 end next to my object, and I'm going to read off the scale to take my measurement. But using my scale, the object could be anything from 2.5 to 3.4, and I would still say that it was 3 centimetres long. So right there, I have an uncertainty of plus 0.5 or minus 0.5. Now, although I said up to 3.4, I'd still call it 3. In actual fact, up to 3.4999999 and so on, I would still call it 3. So at this end of the ruler, I've got an uncertainty of plus or minus 1 centimetre. And of course, at the other end of the scale, I've got the same uncertainty because I'm taking a measurement. I'm using two judgments at both ends of my ruler scale. Adding these uncertainties together, using a ruler with a resolution, i.e. the smallest division of 1 centimetre, I have an uncertainty of plus or minus 1 centimetre. And of course, the same would be true for my protractor. I've got to line up the 0, I've got to line up the other end, take my measurement, and therefore it would be plus or minus 1 degree. Because 1 degree is the resolution of this instrument, because 1 degree is the smallest division on the instrument. Let's now consider a thermometer. A thermometer is where we take a reading, and let's consider that the thermometer measures to ½ degree. In other words, it's graduated to ½ degree, and that is what we call the resolution. We're only making a judgment at one end of the instrument, and so therefore our uncertainty is going to be plus or minus ½ degree. So a reading is plus or minus 0.5 of the smallest resolution of the instrument, whereas the measurement is plus or minus 1 of the smallest resolution of the instrument. Let's now consider where we take a measurement and then we expect something to change and we measure it again. This of course happened in practical 3 when we looked at measuring the water potential of a plant tissue. We took some potato chips and we measured their mass before and we measured their mass after. We will have had uncertainty before and we will have had uncertainty after. We actually have to add those uncertainties together when we display our final result. In this example, we've taken a reading, and with a reading, it's plus or minus half of the smallest resolution. But that was for before. We also need to add plus or minus half of the smallest resolution for after. And the smallest resolution of the digital balance was 0.1 gram. Half of that is 0.05 grams. So therefore I need to double that and find that my minimum uncertainty for the whole experiment is plus or minus 0.1 gram. So at some point you need to go back to your lab book, to practical 3, and make reference to the uncertainty. Of course, in assessing uncertainty, there are a number of issues that have to be considered, including not only the resolution of the instrument, but also the manufacturer's tolerance on instruments, the procedures that you adopt, and the size of the increments available. However, what we can assess from the instruments that we use and the resolution is the minimum possible uncertainty. A good way to make comparisons between uncertainties is to look at the percentage comparison. Now that's easily done. What we're going to use is the uncertainty divided by the value and then we times by 100. But of course, if you've got repeat measurements, then what you want to do is look at the uncertainty for your mean value. So again, you could go back to practical 3 and make adjustments in your lab book. So how would this appear in an exam question? Well, again, we need to be clear. Are we looking at a reading or are we looking at a measurement? And even within that, are we looking at a change in a reading, for example, a temperature increase? Or are we looking at a change in a measurement, for example, when the potato became heavier or lighter? If we're giving a reading in an exam question, we're looking at the last significant figure, because this is likely to represent the resolution of the instrument used, unless, of course, we're told otherwise. If we're told in an exam question that a temperature reading is 18.7 degrees C, then the instrument reads to 0.1 degrees C. So the uncertainty is plus or minus 0.05, i.e. half of the resolution. However, we need to be careful how we represent this. The total uncertainty is 0.1. But if we're going to precede our uncertainty with plus or minus, then it needs to be half of that value. So in an exam question, imagine we're told that a person excreted 1,660 milligrams of creatine in 24 hours. We regard the last significant figure of this number and assume that the resolution of the instrument was 10 milligrams. And of course, we don't know without any more detail whether it was a reading or a measurement. So therefore, we assume it's a measurement, remembering that a measurement is plus or minus the smallest resolution. Therefore, in this experiment, our uncertainty would be plus or minus 10 milligrams. So how can we reduce uncertainty? Repeating our experiment gives us more data, and that enables us to identify anomalies. And in some circumstances, it's appropriate to disregard anomalies or outliers. However, at other times, it's really important to include them. So consider a drug trial. 1 person in 1,000 has side effects. It's really important to record those side effects. Another way of reducing uncertainty is to change the measuring procedure. For example, if you needed to measure the thickness of a leaf, by measuring the thickness of 10 leaves together, you'd calculate your uncertainty, but then you're able to divide your uncertainty by 10. So how might this appear in an exam question? If a potato is placed in water and its length changes from 14 millimetres to 15.6 millimetres, calculate the percentage uncertainty. If we're talking about length, then we have 2 judgments. So we're looking at a measurement and we're looking at the smallest resolution, which is in this case the 0.1 of a millimetre. If we were just looking at a reading, we'd be looking for half the smallest resolution, and that would be 0.05 of a millimetre. But with a measurement, we've made 2 judgments. So 2 lots of 0.05 of a millimetre, equals 0.1 of a millimetre. And so we've done this twice, when we measured it before and when we measured it afterwards. In fact, it's like we've got 4 times the uncertainty. The question wants us to work out the percentage uncertainty. So we use our uncertainty, which is 0.2. We divide it by our value, which was our change, which was 1.7. And then, of course, our answer is plus or minus 12%. So now go back through your lab book, look at the practicals you've done, and see if you can comment on the uncertainty and the percentage uncertainty. This will stand you in good stead if you get an exam question on this.